Hi, we are Team 5, and this is our presentation for the attention detection with EEG acquisition.
Now, going through the presentation, first we will introduce the topic by giving an overview of the challenge presented to us. Then we want to attack the methodology with which we attacked the challenge, the results we obtained afterwards, the AI used during the challenge, and finally the conclusions. EEG acquisition allows us the understanding of brain activity. Some research suggests that certain frequency bands, such as theta and alpha, can map attention levels. The objective of this challenge is to design a system that is able to identify attention and inattention levels in a healthy subject through feature extraction of an EEG during a numbers group test. Our hypothesis is that there is a significant relationship between the EEG signal patterns in the alpha, beta, and theta band during a Stroop numbers test and the attention levels. We think that using a neural network model trained in MATLAB based on the participant's response accuracy can help us to accurately classify these attention levels. Now, the first step in proving our hypothesis was to acquire 5 healthy male subjects in the age range of 20 to 25. In total, we did 9 trials, which means almost 2 trials per healthy subject. We used 8 different electrodes for the signal acquisition. First, the FZ, F1, F2, F3, F4 electrodes, and then the central electrodes of CZ, C3, and C4. The software for acquisition was the USB-G.amp. And the software with which we did the numbers group test was the Pebble software. Now, the numbers group test is a test that shows you a set of identical numbers, but in a different frequency. What does that mean? It means that, for example, we get on a display the number 2, but 2 times. This would be a congruent Stroop test. And the incongruent Stroop test would be if we see the number 2, but 3 times. And what do you have to type in? You have to type in not the number you see, but the number of times you see that number. This is why we have different concentration levels or attention levels required for the incongruent test or for the incongruent Stroop test and for the congruent one. Now, we did, as indicated before, the attention and inattention trials, and 1 minute pause in between these attention or inattention trials. Now, we did 5-minute pauses in between the acquisitions while doing 2 acquisitions per patient, which resulted in, well, in this case not 10, but 9 trials in total.
After creating the database, filtering was then used for the filtering of the signals between 4 and 30 Hz. This filtering then allowed us to extract the features of alpha, beta, and theta, along with other features we will discuss further. High pass and low pass filters, used with filtrip, also allowed us to remove the movement and noise artifacts. And after filtering, the signal was cut into attention and inattention trials based on the markers. After the signal filtering, we then proceeded to extract the features with 2-second windows and a 50% overlap in between windows. This allowed us to accurately extract all the features we used. These features include average power in theta, alpha, and beta frequency bands, 24 features, 3 per each of 8 channels used. Then we extracted the band ratios of theta alpha, alpha beta, and theta beta, one of each per channel, the total power in every channel, then the variance per channel, total power and energy through time, each per channel, that's another one, and frontal asymmetry. This is the power difference between electrodes F4 and F3. A total of 59 features was extracted for the characterization of attention and inattention. Now, for the attention level prediction, we used a neural network consisting of multiple layers of nodes or neurons, in this case perceptor neurons, which were used for supervised learning tasks such as classification. In this case, we classified the features extracted. The structure consisted on an input layer, two hidden layers of 36 and 16 neurons, and an output layer. Their learning was done with a forward and back propagation as well as error calculation. The training was used with a sigmoid activation, a sigmoid formula, and then after training and prediction, the evaluation was done with a five-fold cross validation in between neurons, as well as an ROC curve to assess the accuracy of our model. These models basically work with an input, a weighted and a bias that decide whether the attention is there or not, and then an output deciding whether there was attention or not.
Uh, During development of this project, artificial intelligence, especially machine learning, play a key role in achieving strong results. Perception-based neural networks provide to be effective for classifying attention levels from EEG data. Additionally, the filter toolbox was essentially for filtering and preprocessing the EEG signals, ensuring clean and reliable input for the model. Together, these tools allow us to automate the classification process and support our hypothesis with solid performance. After training our model with EEG data, we achieved an accuracy of 88% using a multiplayer perceptron neural network. This result allows us to conclude several important points. First, even though the perceptron is considered a relatively simple type of neural network, it provides effective in identifying attention levels. This highlights that even basic architectures can yield reliable performance when combined with appropriate preprocessing and feature extraction. Second, tools like MATLAB and FieldTrip were essential for processing EEG data. These platforms enable us to filter signals, extract frequency-based filters like delta, theta, and beta, and prepare the data for training the neural network. Overall, the results validate our methodology and show the potential of using neural networks in cognitive state classification based on EEG signals. First, let's focus on feature importance. Alpha, theta, and beta waves play a crucial role in classifying attention levels. These bands are known to reflect concentration and mental activity. After classification, we observed that a reduction in power within these bands corresponds to low attention, whereas higher peaks indicate in great focus. Now, regarding comparison with other studies recently researching using EEG and stroke test has shown that our attention states have been currently classified using features, especially delta, theta, and theta. Activity, various machine learning models such as MLP, SVM, and LSTM have achieved accuracy between 73% and 96%. Our model reached an accuracy of 88%, which balance sincerity and specificity, which place it in with its valid range. This confirms that the combination of frequency domain filters and neural network is effective for cognitive state detection. After implementing the machine learning algorithm and analyzing both our data and previous literature, we can confirm that our hypothesis is supported. Properly extracted and processed EEG characteristics, especially filters from alpha, beta, and theta bands, can significantly contribute to the classification of attention levels during text executions. This conclusion aligns with existing studies that highlight the effectiveness of these frequency bands in detecting cognitive states during tests like stroke. Therefore, we can state that the hypothesis is accepted as our findings validate the use of EEG and machine learning for attention quantification.